Good morning. I'm sorry that I cannot be with you here today, but I am here in spirit, so hopefully that counts for a little bit. We're going to pick up on our notes where we left off yesterday. We had pretty much gone through that first example. We were on part C, where we decided that the L value was that numerator. And so to find when the elastic was growing the fastest, we would have to cut that L value in half and then set it equal to our equation to actually find the T value. So if you did that, you should have gotten the year 1982 because you get a T value of 82.765. Okay. So here we go. At the bottom of the page, I do have a reminder for you that the AP exam likes to try to trick you, you know from experience. So you need to be able to work with these two equations, but a lot of times they're going to, let's get my ink on here, they're going to disguise that dy dt equation where maybe it's not factored, or maybe it is factored, but it doesn't look like L minus y, and so you have to do a little bit more factoring. So you just need to pay attention and make sure that before you begin working your problem, if you have dy dt, it needs to look like that, where there is a y on the outside and an L minus y inside of those parentheses. Okay, so let's go ahead and look at our next example here. Okay. So we have dp dt given to us, and it looks like we do have the correct form. And this is modeling the growth rate of a population of bears in a newly established wildlife preserve, okay, where T is measured in years. So before we do anything else, okay, instead of Y, we have P in this example, P for population. Our L value is 100, and our K value is 0.008, because this is KY times L minus Y. Instead of Y, we have P. All right? So, what is the carrying capacity for the bears in this wildlife preserve? Turn to your neighbor, tell them the answer. I hope you said 100 bears. L is our carrying capacity. That is what we are going to approach as time goes to infinity. Part B, what is the bear population when the population is growing the fastest? Turn to your neighbor, tell them the answer. The bear population when we are growing the fastest is L over 2, 50 bears. If they ask you when the population was growing the fastest, you would have to take that 50 and set it equal to your original equation, which we don't have right now, so we won't worry about. But please understand the difference in the wording. Okay, what is the bear population when it's growing the fastest? That is the L over 2. What is the rate of change of population when it is growing the fastest? Okay. Rate of change. Rate of change should be a trigger word for you. That means we are talking about the derivative. dp dt evaluated at 50, whoops, not T. Evaluated at 50 bears. So when P equals 50. So when we plug 50 into our rate of change, or our derivative, we have 20. And what is our label? I hope you said bears per year. It is a rate, dp/dt, so bears per year. This is the fastest rate. After we hit 50 bears at 20 bears per year, this rate will begin to slow down. on? Okay, so here we have a population according to the logistic differential equation. Notice how this does not look like K times Y times the quantity L minus Y. So we need to get it to look like that before we go any further. So not only do we need to factor out a P, but we also want whatever is right here to just be an L value. So we don't want it to have, we don't want, not only do we want this to be an L, I guess I really should be talking about, we want this to be L minus P. So we want this coefficient to be factored out as well. Okay, so we need to factor out 0.002 P. Okay, that way we are left with, when we divide out 2 1/1000ths out of 2 tenths, we are left with 100 minus, when we factor out 2 1/1000ths P out of 2 1/1000ths P squared, we're left with P. That was the goal. We need this to be P with a coefficient of 1, which is why we factored out the 2 1/1000ths. So now we can identify our L value to be 100 and our K value to be 0.002. Okay? Our L value stands for our carrying capacity. So no matter what our initial condition is, our population, excuse me, yes, our population will always approach our carrying capacity. Okay? So even if the initial condition is 0.5, the limit as t approaches infinity is our carrying capacity. Even if our initial condition is 0.60, the limit as t approaches infinity is our carrying capacity. Even if our initial condition is 0.120, I know that's bigger, but since it's bigger, we're going to look at the picture, okay? Our carrying capacity is still 100. Now, what do these graphs look like? Okay, Bailey, this is a question you are asking today. Depending on the initial condition, our picture may not look like the one on the front. Okay, so here is 50, here is 100. Why am I, oh, that was not a very good picture. Why am I making a big deal out of where 50 is? 50 is going to be where what is located? Turn to your neighbor and say it. The inflection point should be at that P is 50. Okay? So if our initial condition is 0.5, then our graph will look very similar to the one that we saw on the front page, where we're concave up, we hit 50, and now we're concave down. We will always approach that carrying capacity. Okay? Now, if okay, I don't have room for my 100, but you know it's there. If our initial condition is above our halfway point, we are still going to increase towards that horizontal asymptote, towards that carrying capacity. We're just not going to have a point of inflection because we're already past that L over 2. Okay. Similarly, we will not have an inflection point with this initial condition. This initial condition is P of 0 is 120. We know that we have to approach that carrying capacity. And so we have to decrease towards that horizontal asymptote. Okay, so here are three different graphs that we could have for our original or for our differential equation. Okay, the one we're going to see most often are ones that look like A, but it is possible for our population to be decreasing like in C, or to be increasing but slowly the whole time. Okay? It all depends on your initial condition. All right. Last example. All right, we have the flu spreading throughout the community, modeled by this differential equation. Okay. It is saying logistic differential equation. Here it is. It is already set up in the k times y times the quantity L minus y. So what I need you to recognize is, first of all, that it's logistic, that k is 0.001, L is 3,000. Therefore, your P of t is going to be your life minus lift equation. Okay? You don't have to use that shortcut, it's just an option. But what we can do is we can plug in our 3,000 over 1 plus CE to the 3,000 negative 3,000 times 0.001 times t, which gives you, I'm going to try to save some room here, negative 3t as that exponent. So now we can use our initial condition to give us our C value. Okay. So we have a Y value of 50 when t is 0. So e to the 3 times 0 is 1. Is because it's e to the 0, right? So if we multiply 1 plus c over, we get 50 plus 50c equals 3,000. We subtract 50 over, we divide by 50. C is 59. Okay, so our equation should be 3,000 over 1 plus 59 e to the negative 3t. That is for when our population starts at 50. Now, for part B, we need to use our solution to find the size of the population when t is 2 days. So P of 2, you're just going to plug in 2. How many people have the flu after 2 days? I'm using my calculator. You use your calculator. Make sure that denominator gets in parentheses. Thanks. seems like an awful lot of people to have the flu after 2 days. For part C, use your solution to find the number of days that have occurred when the flu is spreading the fastest. So we know that 3,000 over 2 is when the flu is, how many people have the flu when it is spreading the fastest. So what we need to do is we need to take our equation and we need to set it equal to 1,500 so we can figure out when our flu is spreading the fastest. When means time, so we need to solve for t. Okay. So I will give you a little bit to see if you can get that on your calculator. You can either solve it with algebra or you can go ahead and use your TA89 and solve it, or use your graph feature to solve it. You should get a t-value of 1.359, and that stands for days. So not even a day and a half, and it's spreading the fastest. This is a very quick spreading flu. Okay. So this is what I need you to do. If you have any questions, try to work together to figure them out. If not, I can answer some tomorrow before we take our quiz, but not for very long. I'm probably only going to allow like 5 minutes before we take our quiz because you'll need all the time. I need you to work on the logistic growth homework that your sub will hand to you. My answer key is on the board. Please check your answers as you go. Please check your work with my work. When you are finished with the homework, you need to show the sub, and they will then give you your quiz review. The answers will be posted online along with the solutions for you to check. The quiz will cover slope fields with Euler's method, separable differential equations along with the y equals c e to the kt included in that, and then this logistic growth stuff. There is only one logistic growth problem on your quiz review because you are doing, I can't remember how many problems are on your homework, but you're doing a handful of them today along with your quiz review, so I did not overload the quiz review with those kinds of questions. Okay, so please work together, work efficiently, and I will see you tomorrow.